Now we have a presentation on convergence of simulation and AI in EV development by Sushil S. Mani, Technical Director, Altair India. Welcome, Mr. Mani.
My name is Sushil Mani, and I'm representing Altair India. And in this presentation, I would like to talk about this convergence of simulation and AI in electric vehicle development. So as you all know, many numerical simulations have been widely used in the engineering domain to do a lot of design validations. But with the recent, let's say, technology developments as far as artificial intelligence and machine learning is concerned, there has been a lot of convergence that we are seeing between simulation and AI, and that is really driving vehicle development greatly. So that is the topic of discussion today. Move on to a quick introduction about Altair before diving onto the topic. To begin with, I would like to talk about our vision, the Altair's vision, as stated by Jim Scapa, our founder and CEO. He states that transform the customer decision making with simulation, data analytics, and high performance computing. And therefore, this simulation, data analytics, and high performance computing, this convergence is what we are seeing is going to transform customers' decision making. So with that quick vision, let's look at some of the broad solutions portfolio that Altair has to provide. We have tools which will help engineers to design, model, and visualize all these complex systems. What are the different EV customers? Who are they? The different customers in the EV space who have been using Altair solutions to model and simulate for the EV applications. We have a range of different OEMs as well as suppliers, which has been listed here. Let's start the discussion on this particular topic of this convergence. And to begin with that, let's say the PCB level to the full vehicle that you see there, right? And currently, what we are seeing is that each of these different disciplines have been modeled and simulated in silos, right? We have, let's say, the electronic or the electrical engineer, we have the fluid dynamics engineer, the structural engineer, trying to model and simulate his particular domain or his particular, let's say, discipline in his world. And there has been no, let's say, interaction between all these different disciplines. And therefore, there is a need now because we are actually looking at these complex integrated systems to have a single platform which will provide engineers to talk between multiple disciplines and help us to do a lot of these complex co-simulations which are needed to model and simulate these, whether it is for motors and controls, embedded, thermal efficiency, noise and vibrations, or safety. There has to be, let's say, a constant communication between each of these different disciplines or domains. What we are coming to is now this global evolution, right? Where we are seeing a lot of these smart and connected, let's say, products, which would definitely need a lot of strong user experiences with integrated controls, electronics, and the mechanical functions that drive the products. And to make this happen, we will definitely need this convergence between simulation, data analytics, and high performance computing, which will allow engineers to massively explore ideas, which will help you to drive the designs, right? So the convergence is what we are seeing, which is going to drive all the design and decision making for these smart and connected products. The product development, or what we call as the smart product development, basically encompasses, let's say, different stages of the product development, right? From the product design stage, where we are at a very early concept stage. We have a wide range of tools which will help engineers and designers to come up with that initial concept. And once you have your design ready, you run a range of different simulations, right from, let's say, the structural simulations to the electromagnetic simulations, the manufacturing simulations, and so on. But these systems, as I told you earlier, are made up of very complex systems, right? It is not just the structural world or just the fluid world and so on. And therefore, there has to be this constant interaction between multiple systems. And what makes that possible is this model-based systems engineering approach, right? And therefore, this particular platform, which will help you to connect not only the 3D models, but even, let's say, the 1D way of modeling these particular physics. And once you are at this particular platform, you will be able to generate a particular C code, which actually goes into the embedded systems. And therefore, we need to look at certain platforms which will help you to do the embedded development. And apart from that, even the software development, we need, let's say, platforms which will help you to manage the devices, help you to do the data storage, and then the stream processing. Apart from that, eventually what we need is a continuous improvement of the designs, right? So once you have modeled this virtual model, as we call it, or the digital twin, we need to actually connect with the physical model as well. And therefore, this connection is possible using smart products, which will help you to connect the physical model with the digital model and then give you real-time dashboards. In this process, there will be a lot of usage of AI and ML, and that is what we'll be able to see in the subsequent slides. So talking about smart product development, what are the different building blocks which make up this smart product development? So as you see on this slide, where there are different building blocks. To begin with, as far as, let's say, creating this simulation driven twin, as we call it, there are tools which will help you to model in the 1D and 3D world, as well as use some of the FMI, FMU kind of mock-up interfaces, which will help you to connect the 1D models with the 3D models, and then generate a lot of, let's say, physics-based data, right? Once you generate this data, you'll be able to use some of these machine learning models that we are talking about and create a lot of these reduced order models, which will help you to predict the performance of these complex systems. So these are the key building blocks which will help you to drive smart product development. So what are the enabling technologies for smart product development? As you see on the slide, we have different stacks which will provide you these solutions. We have the data analytics stack, which comprises of the data automation and collaboration, which allows engineers to read in a lot of data, a disparate, let's say, data set, cleanse that data set, and then use that for further predictions using some of the tools that we provide in the data mining and predictive analytics stage. And then even the real-time data visualization tools, which are part of the data analytics stack. We all know very well about the simulation stack, which is what we have been using traditionally in the simulation world, the physics-based simulation tools, right from optimization, DOE, the multidisciplinary system simulation tools with the help of the math and system-based modeling techniques. And then finally, at the bottom, you see the IoT stack, which comprises of the smart product development tools, the IoT applications that you can develop as part of the IoT stack, and then the embedded systems. All these three put together will actually help us to build all these complex systems and then build the digital twin as well. Moving on, meaning let us look at certain applications which basically help us to get this convergence that we are talking about between simulation and AI or machine learning, right? Modeling technique is this model-based systems engineering approach, which allows engineers to model these complex systems in a building block which is workflow based. As you see here, there is a 1D signal based modeling technique. We can also build these complex systems and then run simulations by using the 1D physical modeling approach. And then we can also connect the 1D models with the 3D models and then do a lot of these co-simulations. And the kind of, let's say, physics that we'll be able to model and simulate are wide ranging. What you're listed here is some of those complex systems, right from multi-body mechanics to electromagnetics. But apart from that, you can also connect to many very varied different physics-based simulations that you would do. And once that is done, this particular platform will also help you to generate the required C code, which can be embedded on your electronic systems. We were talking about this MBSE approach, the model-based systems and engineering approach. And here is an example which shows you a particular model which has been generated in this workflow. which talks about how you can create a complete block-based approach of having to give a certain drive cycle as an input, and then let the driver controllers, the electric motor, as well as the inverter, converter, and the battery pack, which is modeled in this 1D world, to help us to take this input, which is the drive cycle input, and then give us a range of different outputs, right from the vehicle range that you can get from the current motor specifications that you have given, to even calculating the state of charge for the battery, right? So this these complex physics that you can model and simulate is wide ranging. And since these are quickly can be generated and run, the solution times are very fast. Another example, which was actually presented by Linod and Bauer, actually give an input as the speed, and then with the rotor positions that they were able to monitor accurately, they were able to really find out the kind of torque ripple that is generated with the accurate rotor position calculations. So as you see there were different sensors that were used in this particular workflow, and based on these different sensor rotor position sensors, they were able to look at how the torque ripples are changing. And as you know, many torque ripples could eventually lead to a lot of vibrations as well as sound being generated, which is not really advisable. So how this workflow was able to rightly get the rotor positions to accurately predict this entire workflow was presented here. Look at one such application where you can actually look at how you can run a lot of complex 3D simulations and generate this training data. And once you create a training data set, then you can actually use that in the 1D world to then do a lot of quick simulations in the 1D world, and build an ROM model, the reduced order model, a predictive model, which can then be used for all your predictions. So just to give a very simple example, what we did was to build a battery cell, and then runs these thermal analysis in OptiStruct, our structural and thermal analysis tool. And given a certain input as current and the heat transfer coefficient, the requirement was to measure the temperatures at 3 different nodal positions. What this will be able to do, this whole platform, is to generate reduced order models, right? And the benefit of this particular workflow is that with very less training data set, you will be able to actually generate reduced order models of very high accuracy. And let me show you this application in detail. So as you see here, the 3D analysis, we have run a 3D analysis of the battery cell, which is actually a thermal analysis, and that becomes the training data set. So there are varying, let's say, current values and the heat transfer coefficient, which comes in as an input, and the requirement is to output the temperatures at these positions, nodal positions, right? So this simulation that you have done in the 3D world goes in as a training data set into this ML model that we're talking about. And then the engineer with this training data set will be able to define the different layers that he has to model in this neural network based ML model, and also define the neurons, right, that we're talking about. And once you define these inputs and then build the ML model, you'll be able to find out the error of the model generated. And if you're happy with the accuracy of the model, then you can use this ROM model that we are talking about, the new ROM, and then bring it back into the system to do future predictions. So as you see at the bottom left, the whole idea is to get this ROM plugged back into the system simulation. The previous slides of the data analytics stack, right? And one of those toolkits there was this Knowledge Studio. In most cases, of course, you will get probably, let's say, simulation data which is available on the fly, but there is probably, let's say, a lot of data that you have generated in the past, some historical data. This historical data can be used to do a lot of diagnostic and prognostics of complex systems. And in this case, here in this particular slide, we actually use this training data of a historical data that you had on this lithium ion battery to create a machine learning model from a training data set, do the scoring as you see in this workflow. This is actually a workflow in Knowledge Studio, taking in a training data set, building the ML models, do the scoring, and if the quality of the model is good, and then use that for, let's say, testing new data that you are pushing in. So get the new testing data here, and then predict the responses from this machine learning model. So in this particular case, as far as the lithium ion battery is concerned, we were able to predict the state of health as well as the remaining useful life almost line on line, as you see on the graphs on the right side. These workflows, meaning the machine learning or the AI workflows, are also now integrated into the modeling and visualization environment in HyperWorks. And that has been really beneficial because you can now do real-time performance predictions using this auto ML or optimization. You'll also be able to create new data sets from this workflow and then leverage this machine learning model in a very simplified workflow in the modeling and visualization tool. So therefore, now for any, let's say, future programs, you can actually use this expert emulation tool, which can do the job of an expert who has been able to do that in the past. So that is one of the key workflows here for different kinds of complex systems. So if I just run this video, you'll see that you can actually go on the Altair One website, and the engineer can then load in the model as well as the results. Once he loads in the model and results, so it's a three-step process. As you see at the top, you need to collect the data. So you need to start with, let's say, the initial baseline model and then generate that data. And once that data is generated, then you basically build the ML model. And once the ML model is built, you can then do the real-time predictions. So as you see here, you can actually start dragging and dropping the, let's say, the model and the results, and then define the drive where you will now be able to run, let's say, simulations on the fly. And once that is done, you can, once you read in the model, you can pick in the design variables, the design parameters, which are going to affect the performance of the system that you are looking at. Automatically, the tool also identifies the outputs that that are generated by the solver. And once that is done, let me fast forward this. And over here, we now have the ML model automatically picked by this particular tool to now do a lot of, let's say, post-processing, looking at variable ranking or sensitivity analysis that you can do a lot of what-if studies, right, with this ML model that has been generated. And then once the quality of the model is good, you can actually go one step forward to do real-time predictions. So the engineer can then go to this particular workflow where he can move these sliders of the design parameters and look at the responses, whether it is a single value or maybe even a curve, right? So as you see here, meaning the design AI platform, which is cloud native, has been simplified to actually help engineers to get in simulation data or create these simulation data on the fly, and then do a lot of these what-if analysis of all their complex systems, and use this auto ML, the machine learning model, to do their predictions. So with this, I come to an end of my presentation. Thank you.
Thank you, Mr. Mani, for this presentation and the knowledge you shared on this platform.